Welcome back to section 10.3. We have 4 videos for this, but it's worth it. It lays hopefully a solid foundation for you in terms of polar coordinates. And then when you go into the last section, 10.4, we'll do the calculus. And by then, if you're graphing well, that goes rather smoothly for you. There's a challenge or two, don't get me wrong. Okay, so this next section is about sketching circles and then sketching what they call limichons, which I put in that order so that this video fits together. You kind of do them the same way-ish, okay? And then the next video will be dedicated simply to rose curves and how to graph those things as well. What we do here, though, helps us with the next video, so here we go. Sketching circles, we need to first of all be able to recognize circles when we see them, okay? So when r is a constant function, well, we've already done something like this, but let's take another peek, okay? If r is equal to, I don't know, 2, then what happens in that case is r is held to be 2 as you spin around. And maybe you're getting a little bit more accustomed to this, but this is supposed to be a circle of radius 2 all the way around, okay, etc. So that's what when you see r is equal to a constant function, that's going to be in your mind. And remember, we changed it into rectangular, and it was x squared plus y squared is equal to, in this case, it would turn into 4. X squared plus y squared is equal to 4. So we did that in the last video. I'll write that down here, last video. This guy would be, square root of x squared plus y squared is equal to 2. So x squared plus y squared is equal to 4, which is exactly that circle. Okay, so burn that one into memory. But here's another kind of circle, right? I might need some room for this, but anyway, it says functions of the form r is equal to a plus or minus sine theta, or r is equal to a plus or minus a cosine theta, I should say. Okay, so let's explore one of these guys. I think in class we did sine, so maybe we'll play around with cosine this time, okay? So let's say that we are looking at, let's see, r is equal to positive, and out here I'll put a 3 cosine theta. Now, there is a way to convert that to rectangular, which I'm going to show you. In fact, one of your show your works is doing something like that, okay? But if we're in a hurry on a test, the first thing I want you to be able to do on the test is look at this and go, oh, it's a circle and I know kind of where it is. Then when you plot a few points, you just nail it down and you're in good shape. A few, as in like 2 maybe. But it takes a memory, and the memory comes from experience and understanding what the heck is going on. So when you're plotting something new, you typically just try a bunch of points to see where it's at. And since theta represents an angle, you typically put in like, well, let me put in angle values like 0, I don't know, pi over 4, pi over 2. Well, let's see where that takes us right now, okay? So, you know what happens when you do this is you may not put the right points in to get a good idea where the curve is, right? But we'll do it anyway. So when you plug in theta, you see what I mean by the ordered pairs are backwards too, by the way? I'm so used to putting numbers on the left-hand side to compute the right, but someone somewhere somehow decided to go r theta instead of theta r. Oh well, whatever. Okay, so cosine of 0, let's do this guy. Cosine of 0 is 1. So 3, say r is equal to 3 cosine of 0, which gives us 3, doesn't it? I'm laughing at myself. Gives us 3. In this case, r is equal to 3 cosine of pi over 4, which is like radical 2 over 2, so it's 3 radical 2 over 2. And then finally, you get here, r is equal to 3 cosine of pi over 2, which really becomes 0. Now, when I do that much, you're not going to have much of an idea of what's going on with this thing. I did call it a circle, so you might have a hint as to the shape, but if you just start graphing now, it may not happen for you. You're going to, okay, let me graph it. I know what I'm doing. I'm going to graph it right here. Okay, so I've got, in my graphing, I've got 3, 0. So in other words, when theta is 0, we go out to 3. When theta is pi over 4, right, it gets a little smaller, okay? You know what? Stewart's method is actually helpful sometimes. He's saying, why don't you teach them this? It might help them. Let's graph r is equal to 3 cosine theta, as if it were rectangular. So now we know it starts at 3 like our first point does, but of course it cruises down and back up to here when you get to 2 pi. So this is pi, and this is pi over 2, and this is 3 pi over 2. And you can see that r is positive but shrinking to 0 when it gets to pi over 2. What I was doing with you guys is, 3 radical 2 over 2 is less than 3 by a bit, maybe this much. And by the time you get to pi over 2, you're at 0. So with these points, you don't know what's going on, but with Stewart's idea of watching it smoothly shrink downward as theta swings outward or around to pi over 2, I'm going to use a different color for my points. Let's use red. We'll start here, and what's going to happen is you're going to get, as theta cruises through those angle values, you're going to get the upper half of a circle. How are you so convinced, Weber? You know why. I teach this stuff, right? Now, okay, so again, what needs to be emphasized, and I'll do this in I guess I'll go back to, I need another color so you can really see this. It's getting kind of busy. But theta is spinning through these angles, but as r takes on different values as a function of theta, they get shorter and shorter and shorter until it cruises down to 0. Okay. In fact, this is in section 4. We would say compute the area within that region. We would integrate from 0 to pi over 2. I'm just saying, because theta, what it does is it maps out this entire region. You go theta, go out r, theta, go out r, and you get the curve itself, the red curve on the outside. So the fanning that you see is just me trying to animate theta, but the curve you get is the red curve itself. Okay? Now, the interesting part is that when theta goes from pi over 2 to pi, we know that now cosine's going to get negative and more negative and decrease down to -1 by the time it reaches pi. Well, where is pi? Well, pi is here. What is theta doing? Theta is doing, it goes past pi over 2 where it's 0, and then it starts moving outward and fanning towards pi, okay? But as it does so, theta, or r I should say, takes on these negative values until when you're pointing in the pi direction, you actually backtrack 3, and you're on top of that starting point right there. So as theta is swooping through, you're going to get small negative, larger negative, larger negative, larger negative, larger, larger, and what happens is you get the lower half of the curve. You get the lower semicircle, if you will. Theta goes from 0 to pi over 2. You are positive in the positive direction. Theta goes from pi over 2 to pi. You go negative, and you've covered the entire circle. It is a circle, believe it or not. Are you sure it's a circle? Yes, I am. This is a show you work kind of thing that you do. Here's r is equal to 3 cosine theta. And the story is, can I convert this to rectangular to prove to you that it's a circle? And the answer is, of course I can. I've practiced. So here's how you convert this to rectangular. You ready? Take a breath. I zap both sides by r. It's a trick from trigonometry that you rarely ever use. Okay? But what happens is you get r squared is 3r cosine theta. And then all of a sudden, those formulas for converting back and forth rectangular to polar kick in, and r squared gets replaced by x squared plus y squared equals 3, and then r cosine theta gets replaced with x. We have a circle. You see the x squared and the y squared? And if you want to see where that circle is, you bring the -3 over, you split it in 2 to 3 over 2, you square it, 9 over 4. And you got this thing. It says x minus 3 over 2 squared plus y squared is 9 over 4. And you notice that the center, therefore, of this circle is 3 over 2, which is 1.5 and 0. And the radius is square root of that, 3 over 2 as well. So the center is 3 over 2, which is 1.5, which is right there. Okay, that point right there is 3 over 2 and 0. And I wanted to just prove it to you that this indeed is a circle. If you convert it to rectangular, you see it. So the Stewart method of graphing this thing to help you maybe visualize what's happening, at least at the front end, that's what you might want to consider doing, is graphing and then seeing where if you really want to dig into this, and I really would think that you'd want to. I know we're at the end of the semester, but this is really cool stuff. Of course, what happens, the story continues, is that theta is going to go from pi to 3 pi over 2, and what he does is he shrinks to 0, but he's negative. So what he does is he scopes out the upper semicircle again, and then finally he cruises through the positives again, right here, bump, 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 and at 2 pi he's back to 3 again, and that happens here, positive, and yeah, you scope out the lower. So in other words, it goes around the circle twice from when theta goes from 0 to 2 pi. Interesting stuff, isn't it? Okay, so that's the circle story. I also have the Lemaichon story, but I really wanted to point out to you a little bit more about circles. If it's r is equal to, say, a positive number, let's just say a, sine theta, this is how you memorize it. You go, okay, if it's a sine theta, the circle, where's the circle going to be? He's going to be up here. If it's r is equal to negative a sine theta, then the circle is going to be down here. I might do another one on Lemaichons. I think I might. Let's stop this video and do another video on Lemaichons. If r is like negative, is positive a cosine theta, well, we just did one of those, didn't we? And so the circle is here, and if that should be a positive a so that it's clear. And if r is negative a cosine theta, then that guy is here, okay? And it reaches out to a in each case. Now, you know, those are the circles that we're concerned about in our class, okay? When we're doing homework, doing areas, tangents, areas between curves, knowing how to graph these circles is important. I think I will stop there. It seems long enough. Let's look. Let's see, where are you? Yeah, that's enough.